What's up, guys? Yeah, so today let's keep talking about algebraic geometry for a variety. Yeah, so I want to, in this video, I want to quickly introduce the next variety called the projective varieties, the next family of varieties. Okay, so previous we have defined, let me just quickly review a affine variety. So the affine variety basically is you can consider polynomial ring and wherever ideal A, which inside this A, right, you can define a zero set, zero of A, which is the points, which is a point which x1 xn such that f x1 xn equals to 0 for every f belongs to A. This is called zero locus. And then you can also define so this is one directions. If you take the sum set, if you take the points, right, you take the subsets of the points. So points akn, if you take a subset of points, you can define I of t, which is the polynomial inside A, such that f of x1 xn is 0 for every x1 xn belongs to t. Okay. So now so previously that one can show that if you do the if you first do the ideal of the set y, and you take the zero set, this will give you a closure. If you first take the ideal and take the zero set, and then you take the ideal back, then you will get the square root of ideal, which is radical of ideal. This is called the Hilbert. So basically, this is the Hilbert-Noster ansatz. Okay, and also the prime ideal corresponding to the irreducible algebraic set. And in general, so in Hartshorne definition, irreducible algebraic set is called a affine variety. But in some literature, that affine variety only defines on when somebody says affine variety, is just just the definition for some point. It's just the points that if there is a polynomial such that a polynomial equal f such that all these points vanish on this polynomial. Okay, so in some case that so in general, one can, due to this Hilbert-Noster ansatz, one can say that algebraic sets will just corresponding to the radical of ideals. So this is one-to-one, okay? One-to-one radical of ideals. Okay, and the prime ideals corresponding irreducible algebraic set basically is, in our definition, is affine varieties. Okay, so one can do the same thing for the projective variety, and this will correspond into the, if you know like more advanced algebraic geometry, let me just say something. In the algebraic geometry, that one first will start the affine variety, and the one can goes to the cosine affine variety, and the one can go to skin. Okay, so skin is basically just if somebody gives you can skin the generalization of varieties. So the heart of the skins that somebody give you the commutative ring with identity, then you can construct the spectrum called spec A, and you can make the topology on it. Okay, and so there's another family that which is called a projective variety. We will talk about the definition, and you can go to Skinner's idea called Proj construction. Okay, and the idea is for the graded ring. Okay, so this one is much more complicated. So I hope I will do this for the maybe next series. Okay, so let's start for some simple thing. Okay, so this video, let's just define the terminology. Okay, so simply speaking, PKN is defined to be the projective space. So projective n space. Projective n spaces over K. Okay, so this one is like also famous in the like algebraic topology or the differential geometry. So one in a, if you view K just R or C, you can, right? For example, you can define P of Rn. So just very easy, you just define it to be so in a, let's say in a differential geometry or in a algebraic topology. So usual definition is that you can take Rn plus 1 and there is x0, x1 up to xn, you identify with lambda x0s, x1, xn. If lambda is non-zero, okay, by this definition, you need to quotient, you need to minus the origin, right? Because origin is ill-defined. Okay, so this basically you just there's a, so basically it's the space, right? And you quotient out you for the same, if there's a lambda which is scale everyone, then you just neglect this lambda. Okay, and the topology in the differential geometry, the topology based on the you can use the quotient topology because original Rn plus 1 has its own topology. Okay, and so some simple fact is that you can check that the PR1 will be the R2, right? You can check its R2 quotient the modulo 0, 0 and the quotient the 1 relation. And a simple exercise, you can check its isomorphic to circle. Okay, and one can do the same thing for P and complex number. So in this case, that in the differential geometry, you can prove that when n equals to 1, that you get the complex manifold, which is the Riemann surface of genus 0, so it's circle. Okay, and one can compute the fundamental group of these things using Mayer-Victoria sequence or however, right? Not Mayer-Victoria sequence. You can Van Kempen theorem, that kind of thing. Okay, but in the algebraic geometry, yeah, we do the same thing, right? So we can define the P and K to be the that's the same definition, right? So we can use we can just say we have Kn plus 1, and then we think that x0, x1 up to xn identify with this. Okay, and we also forget about the 0, 0 points. Okay, so we are not allowed to use, if there are all zeros, this is ill-defined. Okay, and for lambda is non-zero. Okay. Okay, so obviously that one can view that P and K is just the A, K, N minus the origin and the quotient. Some just do some quotient. Okay, and for x0 let's use a0, a1 up to an is called point. Okay, so one can start and then one can define S to be the polynomial ring to be K of x0s, x1 up to xn. Okay, so we view S is a Grady ring. Okay, so what is Grady ring? Grady ring means that your ring can be decomposed into for every elements, you can decompose into direct sum, RD, and usually D, I think D must start from 0 to something. I mean, in general, you can know infinity, and you have satisfied Ri, Rj. So any two elements in the I component, J component multiple should be a subset of Ri plus J. And this one is called the degree D element, degree D component. Degree D component. Okay, so obviously that the polynomial ring is a Grady ring because this is decomposed with degree 1, degree 2, degree 3, or degree 0, and the degree is defined to be the highest power. Okay. Okay, and okay, and so one can write S in terms of SD, D greater or equal to 0, and then also Si, Sj. S is a subset of Si and Sj, and the element. So the element of SD is called a homogeneous element. So basically, this is the terminology like homogeneous polynomial, right? For example, xy plus yz plus xz is homogeneous, but xyz plus x is not homogeneous because it's degree 3, degree 1. For these three terms are degree 2. It's called a homogeneous element. Sorry, it's called homogeneous. Yeah, element homogeneous element. Okay, and yeah, so we have another quantity which is important. If A is ideal of S, is called the homogeneous ideal. Homogeneous ideal. If A is a direct sum of A intersection with SD. Okay, so this definition is somehow hard to understand what the hell is going on. Okay, but the idea is that the homogeneous ideal means that your A, right? Every component your A is constructed by one homogeneous component. Okay, so for example, I think this example is very easy, right? So for example, if your A is let's say is ideal generated by x squared, xy, y, z, xz, xyz, z cube, right? Each one is a homogeneous element. So this one is a homogeneous ideal. And if your A is basically x squared plus x, let's say y, then this one is not the homogeneous ideal because this one is not the homogeneous element. Okay, so another simple definition is that you can check that A is homogeneous ideal if only if A is generated by homogeneous element. Okay, this is simple definition. You can try to prove, but it's stupid. Yeah. Okay, so now right, so now we can define a homogeneous polynomial. Homogeneous polynomial of degree d. So we say f is homogeneous polynomial of degree d if f lambda a0, lambda a1 up to lambda an is lambda to the d, f a0, a1, an. So basically just very stupid, right? For example, if d is 1, you can define, for example, you can say your xyz just to be x plus y plus z. Yeah, so basically everyone is degree 1, right? So you can check this. D equals to 2, you can define your fxyz. There's an example that you pick xy or whatever, right? Any degree 2. Okay. Okay, so now you can define zeros, right? As our affine varieties. So given f, one can define z of f to be take the points in the pkn such that f of p is 0. Okay, this is for homogeneous ideal, for homogeneous polynomial. And okay, so if T is a set of homogeneous element, T is a set of homogeneous element or subsets, T is a homogeneous elements of S, then one can define the Z of T to be the zero locus. So it's all the points. F of P equals 0 for every F belongs to T. Okay. So now you can also define, yeah, okay. So simple definition. If Y of Pn is called the algebraic set. So this is the same as the affine variety, right? Algebraic set. If there is a T, which is homogeneous, so I don't want to keep writing homogeneous. So when I write this, I mean homogeneous. If there is a homogeneous subset T, such that Y is a Z of T. Okay, so okay, so fact, right? So fact as before, as the affine variety, one can show that if T1, T2 is subsets, you always have T2, the trivial relation. And then you can also show that, yeah, okay. And also you can also show that the union of algebraic set is still algebraic. Okay, and also you can check the intersection of any family is an algebraic set. Okay, and you can also empty and the whole space. So whole space, this means P and K itself is algebraic set. These are all similar as a affine variety. So you can use the zero. I think you can just using the locus, the property of zero locus. For example, you can ask what is this, right? And also you can ask what is the, yeah, basically you can do the same thing. You can ask what is this. So you can ask what is the, you can ask what is this, and what is this. Okay, and I think this is the same as the relationship in the affine variety. So you can check that this give you the same thing. Okay, for example, let's say this is just, you can check this, right? Just this, and and I think this one will give you the Z T1 union T2. Okay, so this proof these two. And the empathy of P and K and algebraic set is that if you just take, for example, you can take T to be the 1, right? So 1, yeah, you can take 1, right? 1 is a 1. Okay, so 1 is non-zero, right? So if you take the 0 set of 1, must be empty, right? 9, no, there's no points. If you take the T to be everything, or the, yeah, you can take T to be whole. You can take T to be whole ring. Okay, generated by whole rings. Okay, so so you can take S itself, then you will get the P and K. Okay, and yeah, so right, so yeah, our definition is that T is a set of homogeneous element of S. Then you can take this P to, yeah, and right, if you take S to be, you can take whole rings. Okay, and then you get everything. Okay, by definition. Okay. Yeah, so that means that we can do the same thing, right? You can define the Zariski topology. So basically, Zariski topology basically say that the closed set is just defined to be the algebraic set. Okay, so now we can define a projective variety. Okay, so projective variety just the irreducible algebraic set. So we can also define the irreducible, right, as the topological space. So irreducible algebraic set in Pn. Okay, so with the induced topology. Okay, now we can define the quasi, right? So quasi projective variety to be just the open set in Zariski topology. Okay, and if Y is a subset of P to N, we can define the I of Y. So in this case, called the homogeneous ideal, which is a subset of S, defined to be the F belongs to S, such that F is homogeneous. So we need to make sure that every element is homogeneous, and F of P is 0. Okay, for every P belongs to Y. Okay, so you take all the polynomials such that, but restricted to homogeneous and I of Y. Okay, and one can define S of Y, which is a coordinate ring, as the affine variety, to be the whole ring quotient I of Y. Okay, and there are many properties that that one can show. But if I have time, I can show all this to you. Okay, so this is basically just a simple definition. Nothing's important. Nothing's important. But yeah, okay. No, and there's a fact that yes, okay. So there's a fact that I think it's also important to mention is that I think there is a fact that to mention is that one can cover PKN using n+1 AKN. So one can cover the projective space by n+1 projective, n+1 affine space. I think this is not difficult to prove. Okay, so maybe let me just quickly give the proof. Okay, so let me just quickly sketch. This is not difficult, right? So, oh, by the way, so in the PKN, right? So the usual notation is that you write in this PKN, usually you will need n+1 number, right? But you will write as this. You will use double column. You will use semicolon. Is this correct? Not. I don't know. I don't know what is the English for it. I forget. Okay, so usually you will use this notation. Okay, so obviously that AKN can be put into the P and K. Okay, it's very simple. You start from x1 up to xn, and then you put into this, right? So otherwise, the easy way to put it, you can map into the first one, x0, you choose 1, right? So it's stupid, you just choose 1. And obviously that things is fixed to 1, right? So if all these are different, then all these are different. Okay. So yeah, this map is 1 to 1. Okay. And right, so one can. So this is the first fact that one can put a affine space into projective. Okay. On the other hand, one can also show this, right? So if you start from this PKN, that you have x0s, x1, x2. You can cover it by, let's say I cover it to be use UI, I from 0 to n, and each UI is defined to be the projective space, the whole projective space. But there's a restriction such that I think this notation is bad, which that xi component is non-zero. Okay. So for this one that I can, so for each UI, right, I can construct map such that I start from up to xn, and on UI, right? On UI means that I restricted xi to be non-zero. Then I can divide every guy to be x. I think divide the xi, so I can make x0 divided by x1, x1 divided by xi, x2 divided by xi, and 1, and xi plus 1 divided by xi, xn divided by xi. Okay, so since it's 1, so you can see that I can delete it. Okay, so now yeah, so now you can see that this map this cover, this map, let's call it phi I. This phi I gives you the UI into the phi A and K. And this map, right? Since xi is non-zero, right? So you can cover it. This is onto, right? For every akn, right? You can put it back here. Okay. So this is onto, and then you can show this is also 1, 1. Okay, so for each UI is one homeomorphic as a topology, you can show that it's homeomorphic to the affine variety the affine space. And then this pkn for each coordinates, you have this such one, and then you can also show that in their intersection there's no contradictions. Okay. Yes. Yeah, I think this is all I want to say of these projective varieties. And yeah. Okay. And I also want to mention there's a yes, there's a yeah, let me just talking about one thing. Okay. Okay, so which means that okay. So there is a special ideal. I think this one is important. There is a special ideal called irrelevant. Okay, that this guy will also show in the project construction called irrelevant ideal in our k x0s x1 up xn. This ideal is just x0 generated by x0 x1 x2 xn. This is usually called I plus. Okay, so I plus has no if you take zero, you cannot, if you take 0 set of I plus, you will not get anything, right? If you take 0 set of I plus, then you get everything 0, but everything 0 is not in the projective space. Okay, so so z of I plus will give you the 0, 0. Okay, so it's not in the projective space. And this one will also show in the project construction. Okay, so now due to this, we need to modify the Hilbert-Nussbaum ansatz. Okay, so let me just finish this video by providing you a statement of Hilbert-Nussbaum ansatz for projective space, projective variety. Okay, so so in a affine variety, we have the two Hilbert-Nussbaum ansatz, weak and strong. And I think for this one, we also have weak and strong. Okay, weak. All right, let's show you one. Okay. So there is a bijection between x and I. So let's say I p k n. So p and k. If S is a subset of the projective space, then the one-to-one map into the ideal of X, or homogeneous ideal of X. Okay, so this is the one-to-one. So this is the algebraic. This is algebraic set. This is the homogeneous radical ideals. Okay. I think there is a fact that homogeneous radial ideal is the same as homogeneous ideal. If I remember it correctly. Okay, E of k x0, x1, xn. This is the same as, this one is the same as affine variety, but except this I plus, this irrelevant ideal, right? Because for irrelevant ideal, the correspondence will give you zeros, all zeros, which is not in the projective space. Okay, the second version is that if I is a homogeneous ideal in the k of x0 up xn, and if so for a weak, right? Remember in the affine variety for a weak, that if the we want to ask what is the case that there's no roots, right? In a affine variety, if there's no roots, that means that that ideal must be the whole ring. So if z of I is empty, you need to first, yes, in a pkn is empty, then I contains I plus to m for some m belongs to n. Okay, so notation is that I plus 0 is I plus 0 defined to be the whole ring. Okay, so this is the like the two slightly different version of Hilbert Natanzas, and I think this can be easily proved by if you know how to prove the original Natanzas. Okay, and I don't talk about the examples. Maybe next videos. See you guys next videos.